All right, good afternoon, everyone. Can you hear me?
Yes, I can.
Okay, good. Can everyone see the screen for the Canvas? Shows the Canvas page, yes? Okay.
Yep.
All right, well, welcome to Cal 3. My name is Robert DiGiovanni. Hopefully all of you caught that video that I sent out through email the other day about the way the class is going to work. If you did not get that, just check your Canvas email, make sure that you watch that. It kind of runs through how this course is going to work. And I'll get into some of those details, I guess a little bit later. Does anybody have any questions just to start off about the layout of the course, the format of the course? We're all okay? At least right now, okay? All right, so let's talk a little bit about the syllabus. I just want to clarify a few things. On the grade, right, you've got these, basically you're going to have a midterm and a final. Those are the only, those are two major exams. The midterm will most likely be a take-home, which, let me just double check here. Yeah, there's nowhere in the calendar, as you can see, there's nowhere in the calendar for an exam other than the final exam date. So we have no scheduled class exams, and that's just because we don't have enough time to get through all the material if we have exams taking up class periods. And that's because we already lost Monday, right? We lost Monday already, so we're shortened to begin with. So we will be rushing to get through everything, but my intention is to finish all the material in this on this calendar all the way through through the divergence theorem. So anyway, okay, so you will have a midterm you'll do at home. The final will be on a Zoom session, and there's details about that in the syllabus. And then I'm going to be giving you 8 mini exams. And these 8 mini exams, let me just kind of explain what they are. So you have homework assignments you're supposed to do for this class, but they're not part of your grade, as you can see. And those homework problems you're going to be doing out of the electronic version of the book. You're just going to be looking at the problems and doing pencil and paper. You're not going to be doing problems and putting your answers into a computer. It's all just for your own learning. And I've already provided all the homework solutions in video format for all of those problems that I've asked you to do. So that can all be found on the main page of our Canvas shell here. So the mini exams, what those are exams that are made up of problems that are slightly elevated problems compared to what you're going to be doing in homework, which means in order to do the mini exams, you need to have done the homework and understand the concepts at a basic level, because the mini exams will push you a little bit harder to really show that you understand the concepts. Now, those mini exams are, take home. You're allowed to work together on some of them. The instructions will tell you. In fact, I just sent everybody the first mini exam. Did y'all get that? So here's the first mini exam. And it says, you may work together on this exam. So if you want to get into a discussion board or something, get a Zoom session going with your classmates, you're allowed to do that. You can ask me for help if you're struggling with a problem. And I encourage you to ask me. And the whole idea here is that these problems are a little bit harder. So I don't mind giving you a nudge in the right direction, but you have to reach out for help with these, okay? Now, with these mini exams, I'm going to give you 8 of them, but I'm only going to take your top 4 as your grade, which means you can do all 8 and I only take your top 4, or you can just decide to only do 4. It's because they're very time consuming. Okay, these exams they should take you a long time to do. So my intention is not to overload you with work. It's just four of these you need to do throughout the semester. So my advice to you would be to do the first, try and do the first one, second one, third one, fourth, just get them out of the way. And that way you're not at the end of the semester saying, oh, you know what, I have to do the last 4. and then realize that you're out of time, that you don't have enough time to finish them. Okay? Does that make sense to everyone? Any questions on that? Okay. Now we'll get to how you submit those and everything else in the format I want. We can get to that. We have time before the first one's due on February 8th, I think, which is more than 2 weeks away. So, and then as soon as the mini exam 2 is, I mean, mini exam 1 is turned in and stuff, I'll probably put out mini exam 2 before mini exam 1's due. And I might even give you that next week. But there will be problems like this says right here. You're supposed to be using concepts 10.1 through 10.5. So until we have finished 10.5, you can't theoretically get through the whole exam, if that makes sense. All right. So that's the way the grade's broken down. And other than that, the only other opportunities to boost your grade in this class is any sort of bonus that I give. And so at the end of the semester, you know, if your grade isn't where you want it to be and you ask me, hey, can I do anything for bonus or anything? I'm not going to offer any bonus. The only bonus I offer is throughout the course. And the first type of bonus is you participating in Zoom and you having your cameras on. Now, that doesn't mean that you have to have your camera on every single day, but it really makes a huge difference when I can see you, and it just feels a little bit more like a classroom rather than just looking at names. So every day when we come to the Zoom session, I have a little Excel spreadsheet here, has all your names. And what I'll do is I'm going to call on you all randomly throughout the lecture. I'll be like, today I'm going to go in alphabetical order. So I'm going to call on Reagan first. I don't know when, but I'm going to call on Reagan. And then as long as Reagan answers, or as long as Reagan is here and participates, whether or not Reagan gets it right or wrong, I'm going to give a participation grade for that. And that can serve as bonus, right? And if your video's on, I'm going to mark it that your video is on. So that way, at the end of the semester, I can give bonus for those of you who were always here and participating, so on and so forth. And then other than that, I might give like quizzes or something like that, but they'll serve as bonus. They'll only add to your grade. They won't. It's like if I give a problem and you don't turn it in or something, it's not going to hurt you, but you know, participating would help you. All right. Any questions on anything? All right. No. So you are all veteran students. You're in Cal 3, so that means you've been through the gauntlet of Cal 2 already. And so, you know, naturally the question is this class harder than Cal 2? Have you all heard anything?
No, not really.
No. It's my opinion that this class is about the same as Cal 2, if not easier, because Cal 2, there was just a lot of new things. And especially if you were doing, if your Cal 2 class went through sequences and series properly, then you saw how that was kind of a big mess, right? Sequences and series. So in this class, we're not doing anything new. There's no new calculus. Like you've already learned how to differentiate in Cal 1. You learned how to integrate in Cal 2. And here we just kind of put everything together and we start to work in 3-dimensional space instead of 2-dimensional space. So we just extend all the ideas of calculus out further to more of the real world, right? Everything you've pretty much done up to this point has been on a flat sheet of paper, but the real world isn't flat. So, well, some people think it is, but you know what I mean? We live in 3-dimensional space, right? So just kind of a general intro, and I don't want to get too deep into this, but you know, Cal 1, if you were to say, you know, what was the main idea in Cal 1, it was probably, you know, visually, it was that if you take a graph, you can go to some point on it and find the slope of that tangent line by just evaluating the derivative at that point, whatever it is, right? And then from that, I mean, you had a lot of other things, optimization, you had related rates, a lot of different things that came out of it. Cal 2, visually, there's a lot here too, but the things I want to emphasize are in Cal 2, we said, okay, take the same curve, and I don't know, this time, let's just kind of like mark some endpoints here, and then we said, all right, we can find the area underneath that curve, right? We can calculate the area. And you can even like rotate that around the x-axis and come up with some weird shape, and then you could find the volume of that. You could even find the arc length of that, of a part of the graph, like how long it is. You know, there's these different visualizations that we had in Cal 2. So in Cal 3, what we do, like I said, we go into three-dimensional space now. We say, all right, in three-dimensional space, instead of having a curve, right, on a flat sheet of paper, you now have almost like a, think of it like a sheet that's kind of like floating out in the wind and just kind of freeze it. And there it is, right? And that's a surface. And so there are a lot of questions that we could ask about this surface. One would be, the Cal 1 problem would be, okay, if you just pick some point on that surface and imagine that you take a little ball and put it on that surface, the question would be, which direction would it roll, right? Like, where would it go? And so maybe depending on the slope, you know, of the surface at that point, you know, it might go down in this direction, or it might go in some other direction. It may go faster or slower depending on where you are on the sheet. So because we're going to be looking at directions of things in three-dimensional space, we're going to have to first talk about vectors. Okay, so the first section we're going to cover in this class is first three-dimensional space. Let's make sure we understand how to draw it, how things work there. And then we're going to talk about vectors. That's our first two topics. But it's going to lead us to something like this. And then after that, we can imagine taking that same surface and just dropping lines down to the ground, and then asking the question, you know, what is the volume of that solid that we have there, right? What is its volume? And then we move on, we do other things. I mean, this is just to give you a general idea of how we've taken the concept of the slope of the tangent line. Well, we kind of have that here. And then the concept of the area under a curve, well, now it's the volume under a surface. So it's just extensions of things we've done. And so that's why I think that the Cal 3 isn't difficult in terms of things that you have to learn that are new. Now, with that said, this class is super, super dense. So there's a lot of material to cover. So even though it may not be no new operations, so to speak, it's a ton of formulas and it's a ton of things you have to keep track of that are difficult as a new student to the subject to kind of organize in your mind. Like, what formula do I use when? I'll give you a great example. In your formulas that I give you for your test, this is just the summary of the formulas that we use for chapter 13. These are just, I let you use these on the test, but to give you some idea of just how many formulas we're dealing with here, how many concepts we have to kind of organize in our minds, right? This is just the chapter 13 formula summary. I'm almost there. 15 pages, 16 pages, 16 pages of formulas just for chapter 13. So it's very dense, and you know, we'll see how it all goes, right? Any questions? Sure. You all look thrilled. Adam, you look thrilled. Adam, what class were you in? I'm trying to remember.
Last semester, I took the same class.
Yeah.
I just had some difficulty, you know, understanding it, so I retook it.
Yeah. Well, hopefully this format will be better, you know?
Yeah, I didn't like the thing without the Zoom, but that's
Yeah.
the only Cal 3 class that I really, you know,
Yeah,
could
no,
take.
I
So
understand. I think it'll go much better this way.
yeah.
But okay. All right. So does anyone have any questions or comments or anything else? before we get going here? No? All right, well, let's get started then. So I have a bunch of notes that are already pre-made, and these can be found in Canvas. Let me go to our course. If you go to course lecture notes right here, this will bring up all the lecture notes that I'm going through. So you can print those out or have them up on a different computer screen. The point is you don't have to copy down all these definitions and formulas. Don't sit there and like, I have to copy all this down, right? And also remember, I'm recording this session, and anything I write down today, I'm going to send to you as a PDF also. So this is more about paying attention and understanding than trying to like get information copied while I'm sitting here. Now, these notes, if you open them, they're just PDF files. That's all they are. They're just PDF, and you just read them. If you're interested in the files in a more interactive manner, in other words, like if you look at my notes here, get to a better example here. Like this example right here in my notes, this is actually three-dimensional, and I can move things around, and I can move points. If you want to have that ability to do that, then you actually have to go back here to our files. I have these things called CDF interactive notes, and these are the actual files that I'm using, but you have to download a player from Wolfram Mathematica website to be able to open these and mess around with them like I am. So if you're interested in that, just send me an email. Maybe I'll email the whole class the link to download the player. You need the special player to be able to open those. Okay? All right, so let's get started with the notes. Evaluate this. All right, we are starting out in chapter 10, and the first section is the 3D coordinate system. So we're moving out of two-dimensional space into three-dimensional space. And so we're going to start back talking about what's called R1. Okay, so R1, so that's like the real number line, R1. So that's a double struck capital R. When we say capital R like that, we normally have thought about the number line, right? Like all real numbers. And so there's really a 1 up here, like an exponent, and that just means one-dimensional space. And that's just a line. So if I say, hey, you know, x equals 2, all right, then x equals 2 would be, you go to your number line. Let's say this is, let's say that's 0. Here's 1, here's 2. Then x equals 2 is a point, isn't it? So this is a point. Only if you're an R1 though, right? If you're an R1, x equals 2 is a point. Now let's move on to two-dimensional space. Okay. So now if I were to write the same equation, but we're now in R2, which is x-axis and y-axis, what does this look like? Anyone know what x equals 2 is?
A line.
A line. It's a line. Now it's a line that has, it's a collection of all of the points on this graph where the x coordinate is 2. So that means, you know, 2, 0 is here, 2, 1 is here, 2, -1 is here. Every single point out there that has an x coordinate of 2 qualifies for this equation, which means that if I move this over, right? Oh, you know what? I'm on the wrong. There we go. This is the one. X equals 2. Here's x equals 2 here. Okay, it's that vertical line. In order to be talking about a point, right? A point in two-dimensional space, I have to give you an x and a y coordinate. So if I wanted exactly to be talking about that point right there, then I would have to write 2, 0, all right? Me writing x equals 2 is not the same thing. So it's just important because, you know, because we are, you know, working in different dimensions of space, if somebody says x equals 2 and says, hey, draw that for me, the response you should have is what dimension space am I in? Am I in R1? Am I in R2? Am I in R3? Because they all have different meanings. They all look like something different. Okay, now similarly, if you write something like y equals 1, right? In two-dimensional space, that's a horizontal line through 1, through y equals 1. So it's going to look like that. Okay. So that's y equals 1 right there in two-dimensional space. All right. Moving along. So in two-dimensional space, this is stuff you should be familiar with because that's all you pretty much have done. We have some equations that we should be familiar with that they basically create a relationship between the x and the y value of the points. So like if we say x equals y or y equals x, that is the collection of all points where the x and the y coordinates are the same, right? Where x equals y. And if you were to draw all those points, you'd create that diagonal line, which we call the identity, right? And so there's very the general form of a line in two-dimensional space is this, right? That's the general form of a line in 2D. But here, here's some others. Here's y equals 3x, y equals negative 3 over 13x. That has a negative slope, so the line pitches down. Yeah, so nothing new here. That's kind of just ancillary stuff there. All right, so now let's get into three-dimensional space. All right, so in three-dimensional space, we've added this third dimension, right? So two-dimensional space is a flat sheet of paper. Three-dimensional space, we come out of the paper. So right now what we're looking at is our traditional XY plane, right? That's our XY plane. So to come out of the plane, we need this third dimension, which actually is coming out towards us right now. So I have to kind of spin this so you can see it. There we go. Yeah, there it is. So let me twist it around here. Hopefully that makes sense there. We have the XY plane is kind of on the ground. And then you have this new Z axis that's protruding up out of the plane. And so now the question would be, what does x equal 2 look like here? Right? So in one-dimensional space, x equals 2 was a line. It was a point. In two-dimensional space, x equals 2 was a line, right? Vertical line. Here in three-dimensional space, what does x equals 2 look like? So anyone got an idea here? Maybe?
It looked like a flat plane.
Like a flat plane. So when we think about all the points here, when we think about all the points in three-dimensional space, we now have three different values, okay? Three coordinate values. We have an x value, a y value, that's our 2D, but now we've added this third dimension of z. So if we were to have the point, let's say 0, 0, 0, that would be the point right here in the middle, right? X is 0, y is 0, z is 0. But if I change it to, let's say 0, sorry, didn't want to do that. 2, 0, 0. Now your x value is 2, right? So on the x-axis, I'd come out 1, 2, there's 2. And then on the y value and z value, I don't go anywhere. So that right there is that point, right? But I'm asking you, what is x equals 2? So someone said a plane, and that's correct. Because it's every set of point, every possible combination of points where the x is 2 and the y and the z values can be anything. And what we refer to these two variables, y and z, we say that they are free. Okay, so x is 2, but y and z are free variables. They can be anything. So I can have anything that occurs on, let's say, that line. We could have anything occurs on that line, like vertically. We could have any of these lines, any of those would qualify as long as the X coordinate is 2. So this is hard to visualize. That's why I have this. It's much easier to see this way. Okay, that's close enough to 2. So there is the plane, right? There's the plane. You can see that every point that lies on that plane has an X coordinate of 2. Any questions on that? So when you look at this, there's some language we want to use here. So this equation, X equals 2, gives you a plane that goes through X equals 2, and that plane is parallel to the YZ plane. Now, what I mean by YZ plane is, let me back this up a little bit. The YZ plane is the plane that goes through the Y and the Z axis. Okay, so that's the YZ plane. It crosses through the Y axis and the Z axis. This, let me take the other one out. This is the XZ plane because it passes through the X axis and Z axis. And then you have the XY plane, which passes through the X and Y axis. So when we are talking about X equals 2, we are talking about a plane that passes through X equals 2. I went too far there, but it passes through X equals 2, but that plane runs parallel to the YZ axis. Do you all see that? Are there any questions on that? Okay, let's move on. Now, in the whenever we talk about three-dimensional space, we actually have to establish a rule about the way we draw our space, and it's called the right-hand rule. Now, before I explain the right-hand rule, I want to illustrate to you why it's important and why we have to do it. So let's go back to two-dimensional space, all right? Let's just start here. Our traditional two-dimensional space looks like this. X is here and Y is here. And what we mean by that is this is usually the positive direction of X and this is the positive direction of Y. Okay, right? That's what we normally mean. So what if somebody came in and said, you know what, I'm a rebel. I don't like your way of doing it. So I want this to be my X positive direction and this the Y positive direction. They say, that's the way I want to do my math. Okay. Well, is the math going to fall apart or is everything going to be consistent? That's the question. Does that changing of the labeling of the axes really matter in two-dimensional space? And the answer is no. And the reason why, and I'll try and illustrate it with this. Let me get my marker here. I don't know how good this is going to come out on. Okay, see if y'all can see that. You'll see that? That is the traditional XY plane, right? That does not look like the second one that this person did, right? But is there any way that I could transform this by moving it around, twisting it, rotating it, that it would look exactly the same as the other one? So just imagine I flip this around, just turn the page over, right? If I turn that page over, doesn't that look like the other person's? Does it? Now it does, right? And all I had to do was flip it over. So it's almost like if this was a wall, the person on the left here that draws it the traditional way is standing on this side of the paper, and the other person is standing on the other side of the paper. So it doesn't matter, okay? Does that make sense? Like it doesn't matter how you label the axes. Let me try and get crazier. What if they were like, you know what? I want to do it this way then. They do it like that. Okay, so now the Y positive is down on the bottom. So here's a traditional one. So how do we make this look like The other one. Let's see. Is that it? It's hard because my camera's reflected. Does that look like the second one now? I think it does.
Yeah.
You know? So I just turned it, right? That's all I did. And I promise you, you can try anything you want here, okay? You can try and label these axes however you want. And I promise you that there is a way that I can flip this or turn this to make it look like your way. And that means that, well, technically, I don't know how many, if there are any math majors in here, but we say that these two renderings of two-dimensional space are isomorphic. Okay, they're isomorphic. They're the same, basically. Now, try and do that with a 3D picture, and you can't. It matters. So if I do this, and let's say, oh, by the way, when you draw three-dimensional space, here's the best way, I think, to do it. Draw a vertical line, and then you're going to draw like an X, but squash it down a little bit. Don't make it like a perfect X. Squash it so that it's short and wide. And if you do that, you can get a pretty decent looking 3D. It's not perfect, but there it is. So here's a way I'm going to label things just to start us out here. I'm going to call this the X positive direction, this the Y positive direction, and this up here the Z positive direction. Now, that is the correct way to do it. That's the way that we all agree to do it. But I want to illustrate with a different picture. I'll do it in red. Someone comes in here and says, you know what, I don't want to do it that way. I don't want to do it that way. I want to do it my way. And my way is maybe Y positive and X positive and Z positive this way. So the question is there a way that we could twist or turn or move it around to make them look the same? And the answer is no, there's not, okay? There's not an isomorphism between these two. And so the math in the space drawn in black would be different than the math that's done in the space in red. Namely things like torque. Like when you calculate torque, you know, the direction of the torque is either in or out. And if one person's working with the black version of 3D space and the other person's working with the red version, then your torques are going to go in different directions. So it's important that we all agree upon something. And the agreement that we have is the right-hand rule, all right? So the right-hand rule works like this illustration. The right-hand rule says this. I don't have it written down in words, but it says, number one, you take your right hand, okay? I remember as a student, I took an undergraduate math class called non-Euclidean geometry. And I remember arguing with my professor about something. And I was like, yeah, I'm using the right-hand rule. And she's like, that's your left hand. I was like, oh, yeah, because I'm left-handed. No, it has to be your right hand, okay? So you take your right hand, and the way you draw the three-dimensional space is this. Your fingers point out the positive direction of X, okay? When you curl your fingers, it should curl towards the positive direction of Y. So you can see here that the fingers being curled around, right? If I curl my fingers in, it goes from the positive direction of X to the positive direction of Y. And then your thumb should always be pointed in the positive direction of Z. Okay, that's the right-hand rule. So let me draw something here. Let's say I do this. All right, let me call on Reagan for the first time here. I'm just going to call on somebody. So Reagan, everybody, I don't care if you get things wrong or if you're confused, that's okay. This is not about humiliating people, all right? It's just to keep you somewhat engaged. All right, so Reagan, do you understand the right-hand rule, the finger, yes? No?
Yes, I think so.
Okay, so I'm going to give you some options here. I want you to tell me where I should put Z positive.
I think it would be where A is.
It's where A is. Does everyone see that? So it's hard for me to show it to you with the Zoom. If we were in a classroom, it might be a little easier, but your hand, your fingers are pointed out this direction. But when you curl your fingers, they must curl towards this direction. which means your thumb has to be pointed out that way. So just play with this on your own. But no matter how you do your X, Y, and Z, you're free to do it however you want, as long as you follow the right-hand rule. So this way is equivalent to this way. It's almost like you just moved around with a camera to a different position. That's all it is. All right, moving along. Right-hand rule. All right, so now that we've got three-dimensional space, right? And notice that on my images, when I label X, Y, Z, it's just understood that I'm talking about the positive directions, okay? So this is definitely following the right-hand rule. So just like in, you know, when you're learning about two-dimensional space, you were taught about, you know, quadrant 1, quadrant 2, quadrant 3, quadrant 4, right? You were taught, why are they labeled that way? Have you ever understood why they did 1, 2, 3, 4 and not like 1, 2, 3, 4? Is there a reason why we do it this way? Is it just to be?
I feel like it has something to do with the unit circle.
Yeah, it has to do with angles. So when you talk about a standard angle in pre-cal, our standard angle always starts out pointing out the positive direction of the x-axis. So as your angle starts to grow, your angle grows like this, right? That's positive angle, it keeps getting bigger, and then it goes around, and then it comes back, and it comes all the way through 2 pi. Well, then naturally you'd like for your quadrants to go through your quadrants in sequential order, right? Starting out in the first, then second, then third, then fourth. So that's why they're labeled that way. Now in three-dimensional space, we have an issue because now we've broken up, we can break up three-dimensional space into how many different sections? It's kind of hard to see. There's going to be 8 different sections. And so instead of 4 quadrants, we now have what we call 8 octants. And so the first octant is anything that lies in this region here. So your first octant is anywhere that your X, Y, and Z are all positives. Okay, so as long as if you pick any point in here, the X, the Y, and the Z all have to be positive. That's octant 1. So I have that information here. Octant 1 information, X is positive, Y is positive, Z is positive. Now, octant 2 is back there. So there, I don't know if you can tell, what's the only thing that's changed? Your Z is still positive, right? Your Y is positive.
Yeah,
X is negative, right? So that's the second octant. The third octant is this one. So now your X is negative, your Y is negative, and your Z is positive. Then you have your fourth octant where your X is positive, your Y is negative, and your Z is positive. So those are your first 4 octants. So it's kind of like the top of the plane, the ground. It's the 4 boxes above it. And remember, those boxes go forever, right, in each direction. And then you have the 4 octants below those. So you've got an octant down here, octant down here, here, and there. So there's your 8 octants in three-dimensional space. Okay, so we've already talked about some examples of surfaces in three-dimensional space. When I was putting x equals 2, right? Here's like the x equals 2 was that plane, right? We have y equals a number is a plane that's like this. Z equals a number would be a plane that's kind of parallel to the ground. Right, so those are examples of some very basic surfaces in three-dimensional space. All right, we're going to sidestep here and talk about something a little off topic, but definitely related to three-dimensional space. So back in two-dimensional space, right, back in 2D, I hope you learned that if you take 2 points in two-dimensional space, let's call this point X, Y, and let's call this point, just for the sake of following the same format, call that point RS. The distance between those 2 points, the distance between those is relatively easy to find because you can just construct a right triangle. And then this side, we can call it, let's say, C, and this side's A, and this side's B. We can use the Pythagorean, right, to figure out what C is. A squared plus B squared is C squared. And A is just the difference, or the distance from here to here. That's just the difference of the X coordinates. So you could say X minus R. And then this distance right here would be Y minus S. Now, you might be asking, or you might be thinking, wait a minute, shouldn't it be the other way around? Like R minus X and S minus Y? Well, it doesn't matter. And the reason it doesn't matter is because we're going to take this distance and we're going to square it, right, in the Pythagorean. And so when you square it, it doesn't matter whether or not it had been positive or negative. When you square it, it's going to be positive. So that's why it's irrelevant. But following this, we know that A squared, that's X minus R squared, plus B squared, which would be Y minus S squared, must equal C squared. And now to figure out what C is, all we do is take the square root on both sides, right? And so that's our distance formula from two-dimensional space. Well, in three-dimensional space, if we have 2 points, X, Y, Z, and RST, and you want to know the distance between them, then all you have to do is use this formula, which is very similar to this one. It's the difference of the X coordinates squared plus the difference of the Y coordinates squared. But now we have this additional difference of Z coordinates squared. And it's actually a good challenge to see if you can figure out why this formula works. I'm not going to derive it here today, but if you mess with this enough, you can convince yourself that that formula must be true. Because you got to remember these points are sitting anywhere in space. So we're not going to derive it. You're just going to take this formula on faith for now. That's your distance formula between 2 points in three-dimensional space. All right, now with that in mind, remember that when you talk about 2D, again, if we were to talk about a circle in two-dimensional space, a circle is just all of the points that have the same distance to the origin, right? So every point that you draw in a circle has the same distance from the origin to that point. So it's the collection of all points that are equal distant from the origin. Well, a sphere in three-dimensional space is the same exact thing. It's all of the points in three-dimensional space that have the same distance from the origin, right? Same distance. So where would it have been? College algebra or pre-cal? You learned that the equation of a circle is x minus h squared plus y minus k squared equals r squared. This is the equation of a circle centered at hk and with the radius of r. Does that look familiar to you all? This equation? All right. So look at in three-dimensional space. The equation of a sphere is very similar to this, isn't it? X minus h squared plus y minus k squared. But now again, we have this additional z piece. Z minus, that's a L, okay? Z minus L squared equals r squared. So your center of your sphere is at HKL and the radius is r. So what would the equation of this sphere be? This would be a little question here. What is the equation of you know what? I have a better idea. Why don't we do this? I'm gonna have you all see. I'm gonna make like 3 breakout groups with you all. I'm gonna give you a problem, and I want you to think about it and see if you all can figure this out. All right. So try and jot this down because you won't be able to take this to the breakout session with you. Let's say that we have 3-dimensional space, right? So we've got X, we got Y, we got Z. All right, so let's say that we have a point sitting here in space, all right? And I'm gonna tell you that that point is the point -2, 3, 2, all right? Here's what I'd like for you to find. Find the equation of the sphere centered at that point, which is tangent to the XZ plane. Okay, so this is a good little illustration of how I've talked a lot here about a lot of little things. Let's see if you can put it all together and figure this out, all right? So I'll give you another second to jot this down, and you might also want to jot, well, I'll write it down, the equation of a sphere. What I'm really hoping is that together in the breakout sessions, you'll at least like break the ice with your classmates a little bit, get to talking. That's the equation of any sphere centered at HKL with a radius of R, and that's what I want. Everyone got it? Let's try this breakout room here. Breakout rooms. I'm going to put a lot of you in there. Well, maybe I'll do 4. I'll do 4 groups. So go ahead and join the room, and then I'll pull everyone back in a few minutes after you've had some time to talk. I'm not going to go and visit the breakout rooms. I really want you all to see if you can figure this out on your own. Help each other out. Just another 10 seconds and everyone will be back here. So did anyone make progress at all? Any of the groups feel like they got something?
Yeah, I feel like we did.
Okay, do you want to share? Approach.
I'm sorry.
Do you want to share kind of the approach and like how y'all thought through this?
Well, when I looked at it, you said that it was going to be tangent to the XZ plane, so that one of the points was going to be 0, the Y value 0, or like the end of the sphere was going
I think your
point, so
audio,
you'd get the radius from that, because the
your
radius would be
audio
the
was
Y value.
You know, I'm losing my internet connection. Hold on. Am I still coming through or no?
Yeah.
Now I hear you.
Okay, now Benjamin, I heard nothing you said. I'm sorry. Benjamin, do you hear me?
Yeah, can you hear me now?
I can hear you. Yeah, it was my internet, I think. It went unstable on me.
Okay, I said that because it was going to be against the, if it's tangent to the XZ plane, that means one of the edges or it's going to be right against the XZ plane and not crossing it. So the radius would be the Y value of the center.
Okay, so yeah, so everyone needs to understand that if we go to this point, -2, 3, that means then parallel to the y-axis, we move out 3, which would be, parallel would be about like this. We move out 1, 2, 3, and then we move Z up 2. I'm gonna have to exaggerate. Here's 1, here's 2, here's where we are, right? So if our sphere is, if that's the center and our sphere is supposed to just touch, this is so terrible, just touch the XZ plane, then that means that the radius from the center to the edge of the sphere must be equal to the distance we walked along the y-axis. And that means that the radius must be 3. Is that the way you looked at it, Benjamin?
Yeah.
Does everyone understand that?
Yeah, that's how I looked at it.
How far away is the point from, how far away is this point from the XZ plane is equivalent to how far away is this point or this projection of the point down here away from the x-axis. So it should be 3 units. So that means you should have gotten x, let me see, +2. So this is H, this is K, and this is L. Sorry about all the mess everywhere. And then y -3 squared plus z -2 squared must equal the radius, which we know is 3 squared. So just 9. That would be the equation of the sphere that has this point as a center and just touches the XZ plane. Now, how would this problem change if I said instead of XZ plane, I said XY plane? What would be the only thing that changes?
The radius,
The radius, right? And now what would it become?
4.
2.
This would become a 4. The radius would be 2, but this side would become a 2 squared, which is 4. Okay. All right, I hope everyone followed that. The next question that I want to ask, we want to do breakout rooms, let's say that we have a sphere. Let's say that the radius of that sphere, I'm going to say capital R this time. Let's say it's 5, okay? And then inside that sphere, I have a smaller sphere that has the same center. And let's say the radius of that one is 2. then we could find the equation. Oh, and let's say that the center here, let's say that that center point is the point 0, 0, 0. So it's the origin, okay? Then we could find the equations of each of those spheres, couldn't we? We could find the equation of each one. But what I'm really interested in is, can you find a way to represent all of the material in between the two spheres? Can we find some way of representing that region between them? So something like this. It's kind of a sphere inside of a sphere, like this. And I'm looking for the region between them. So I'm going to have to kind of cut this in half so you can see what I'm talking about. I'm talking about that region between them. So it's kind of like a coconut, right? It's got like this outer shell and an inner shell, and it's got this coconut flesh in between. And then the inside, well, let's just say it's hollow, okay? So is there a way that we could somehow represent all the points that live in here, that live in that region, right? So that's the question. So maybe before we do that, it might be easier if we look at this two-dimensionally. Like, let's say we had a two-dimensional problem, and we'll get back to that one. Let's say that we had a circle of radius 5, and then an inner circle of radius 2. And we wanted to know everything in between here. Well, we know that the equation of the outer circle would be x squared plus y squared is 25. And we know that the equation of the inner circle would be x squared plus y squared equals 4. Is everyone clear on that? Just using the general equations? But we want everything in between the two. So anyone have an idea of how we might be able to make a way to think through this, to come up with a way of representing all this stuff in the middle, all this stuff?
It might be a long way, but you can take the area of the inner circle and the area of the outer circle.
Okay, so what I think you're thinking is, how do I find that area? But the question is not find the area. The question is find a way of representing these points. Like if this equation right here consists of all the points that satisfy that equation, right? And the equation here represents all the points that satisfy that equation. What I'm trying to see is if you can come up with a way of representing all the points in this green region using some sort of expression to do it.
Inequalities?
Yeah, we can use an inequality. So the one way to look at it is this. We want the outer circle. We want a circle right inside of that, in another circle inside of that, another circle inside of that. All these circles, all the circles inside until I get to the one in the inside, right? The one with the radius of 2. So what I want is all the points x squared plus y squared that are less than 25 but greater than 4. So as long as the x and the y that you pick satisfy being less than 25, it'll put you inside the outer circle. And as long as those points are also greater than 4, it'll put you outside the inner circle. And so this represents the green region. Now, if I wanted to include the edges, I would just put equals underneath those inequalities, and that would include the edges also, all right? So with that in mind, how do we represent the inside of this coconut? Same thing, right? Same thing, use an inequality, but this time we're gonna have to use the 3-dimensional version, which is x squared plus y squared plus z squared. That must be less than 25 and greater than 4. And that should give you all the points that live inside the sphere, the outer sphere, and outside the inner sphere. All right, let's talk about, were there any questions? Okay, how about this? How about I just want to talk like in words. Can somebody describe to me what this looks like. That's a Z. So think about it. Should I call on somebody? Yeah, maybe I'll call on somebody. I'll let you think for another 10 seconds. Is Alberto here?
Yes.
Yep, you're there. Okay, I see you there. Okay, so I just want you to talk through this. I'm not expecting some like really nice mathematical answer here. Just like in layman's terms, can you visualize and kind of explain to me what that inequality means in three-dimensional space?
It would be a cube
Okay,
at the z-plane of 2, but
Okay.
going up.
going perfect. Okay, so what we have here, let's say this was z equals 2. Okay, if that was z equals 2, it would look like this. Got to go back here. Here we go. Z equals 2 is right there. That's z equals 2. So it's all the points that have a z coordinate of 2, right? Now you said, Alberto said the z plane. The way that we should say this is a plane that is parallel to the xy plane. So it's parallel to the ground, but it's been moved up 2, right? Okay. Now, but you said a cube, right? So I think what you meant by that is that because it's an inequality, it's everything above this too, right? All the points above this. So I understand why you're wanting to say cube, but technically it's not a cube because this plane the plane actually continues in each direction, right? So this plane continues this way forever, and this plane continues that way forever, and that plane continues that way forever, right? So the way you can look at it is like, imagine that the earth was flat, right? Imagine it was flat and it went forever in each direction. This would be like a cloud, like a layer of clouds, let's say 2 miles high, that went in every direction and just went up forever. Okay, just like this huge thick blanket, that an infinite blanket in every direction that's 2 miles high. Does that make sense? So what we call that is a half space, because the space, three-dimensional space, is this huge thing, right? This is like half of the space. Even though it's raised up 2, it's still technically half because you've got infinity in each direction, but it's like, it's a huge chunk of the space, right? That's taken up. Okay, good. How about, let's see if there's another one. Okay, yeah, we'll do this one. So how about this? How about x is greater than or equal to 1 and y is greater than or equal to 1? So let's see, what would that look like? So here's x, using the right-hand rule here. Let's say that this is x is 1. Let's say this is y is 1. So if x is greater than or equal to 1, that's going to be this plane that's parallel to the YZ plane. But like Alberto said, it's like this infinite cube that goes out the Z axis. And then you've got another one over here, and you're looking for where they hit each other. So look, I can remember when I took Cal 3, okay? I can remember vividly the auditorium I sat in. There were like 200 seats in there, but there were only like 30 students in there. And I can remember my professor Oh my gosh. I'm ashamed of myself that I don't remember his name right now. Okay, it'll come to me. But I can remember trying to learn Cal 3 with just him drawing on a chalkboard. This is like before computers were really good at animations. Cal 3, trust me, if we didn't have computers, Cal 3 would be much harder. But because we can visualize things, it makes it much easier for us. So let me come back to this. Let me do X is 1. Y is 1. Okay, so X is 1 is this reddish one right there. And Y is 1 is the greenish one. And we want to be greater than, X is greater than 1, so it's everything out this direction. But then we want the Y to also be greater than 1, so it's everything out this direction. So it's kind of like this boxy thing here, but it extends out forever in each direction. Does that make sense? It's hard to draw on three-dimensional space on a flat sheet of paper. It's just hard to do.
I have a quick question.
Yeah.
How come it's only that, like, I know it's not a square, it's like infinitely going out, but how come it's just that one piece and not like the rest of the plane?
You mean like on this backside?
Yeah.
Okay, because when I wrote down X greater than or equal to 1, comma, Y greater than or equal to 1, this symbol is an and, which means that it's got to be this and that at the same time. So your X value has to be greater than 1. At the same time, your Y has to be greater than 1. So any point back here would have, or anything in this little region in here, your X would be greater than 1, but your Y would not. Does that answer your question?
Yes. Thank you.
Okay, good question. Yeah, if this were an or instead of an and, that it could be one or the other, then we would include everything here and then everything over there on that side too, and it would be similar but not the same. All right.
So then, is that a quarter space then?
Yeah,
Do
so
we call that a
still,
quarter
that's
space?
still called a half space. I know that seems weird, but it's still called a half space. And the reason why is because let's go back to two-dimensional or one-dimensional space. It'll be easier if I say one-dimensional space. Okay, so let's say I take the number line and I tell you, okay, start here at the number 1 and only pick the points that direction forever. Okay, just those points. You could argue that's still half of the line, because there's an infinite number of points in that direction and there's an infinite number of points in that direction. One unit over doesn't make a difference when you're comparing an infinite number over here to an infinite number over here. It's still like half of the space. Are you satisfied with that answer?
Yeah, I get where you're going.
Yeah, it's not real precise terminology. When you say half space, we don't mean literally half. We just mean like
Half of
not
infinity.
the whole space, but it's a huge part of it. So yeah.
You're saying infinity makes a point arbitrary.
Yeah, it makes one measurement unit over doesn't matter compared to the infinity. They're equivalent. All right. Let's see, I think that's it for 10-1. Yeah, that's it for 10-1. Let's see, we still got a little bit of time. So you all doing okay? This is all just introduction. So 10-2. Vectors. All right, so vectors. Now, for those of you who are math majors, you'll learn later that a vector is not exactly what we're going to do here, all right? A vector, from a mathematical perspective, a vector is actually something very arbitrary. Here, vectors are going to be numbered, like numbers inside of these angled brackets. But for pure math people, a vector could be made up of functions, and it's a more there's a more general definition for a vector. What we're doing is the traditional definition of a vector, the way it's used in physics and engineering. Okay, so what is a vector? A vector, okay, or vectors for us, are objects that have two main properties. They have a magnitude and they have a direction. Okay, they have a magnitude and they have a direction. So that's what a vector is. It's something that has magnitude and direction. That's it. Now, when we talk about the magnitude, we call that the length of the vector, or we may also refer to it as the norm of the vector. And the direction is just, of course, the direction in which it points, the way it points. So in two-dimensional space, okay, see in R2 here, in R2, the way we represent vectors is with this arrow. Okay, so you have an arrow, we have a tail, what we call the tail of the arrow, and then we have the tip of the arrow, and we can pretty much change its length, and we can change its direction that it points. All of these things are vectors, all right? Now we use some notation. You know, if we want to call this thing vector, we'll call it V for vector, right? We use the notation V with this half arrow up above it. So that's like an arrow, but we've cut off the bottom half, okay? So that's the way we notate a vector. In most textbooks, well, some textbooks use this little half arrow. Other textbooks, what they do is they write the letter V in bold. The problem is when I'm writing, I can't write in bold easily. So I will always notate a vector with this little half arrow above it, all right? This is important because if I write X down versus X, these are completely different things, okay? X here is the traditional college algebra variable X, and it usually represents a real number, like X is 2, X is 5. It's a number. This is a vector. That means it has to have a length and it has to have a direction. This doesn't necessarily have to it doesn't have those same qualifications. So this is what a vector looks like in two-dimensional space. Any little arrow that has length and direction. Notice the point of the arrow matters, right? So like, let's say, let me put that point right there, and let me put this tail here, right here. Okay, that vector right there has a certain length and a certain direction. If I flip these over and put the arrow here, the tip here, and I put the tail here, that is not the same vector we just had. Does it have the same length? Same length,
Yes.
but the direction is now different. So those aren't the same vectors, right? So it's two things that have to be the same in order for you to say two vectors are equivalent, they have to have the same length and same direction. I'm going to illustrate that a little more here. Oh, in three-dimensional space, that's a little harder, but in three-dimensional space, imagine you have a vector that's pointed somewhere, right? It's got a tail, it's got a tip, right? It's got a length. Now, direction in three-dimensional space is harder. Would you all agree with that? Think about this. In two-dimensional space, I think it would be easy for us to come up with a convention to find this angle. Like we could say, all right, imagine a dotted line here, and we could all say whatever that angle is, we'll call it theta, that's its direction, right? Because we have a natural place to orient everything, kind of off of the x-axis. But if we get to three-dimensional space, not so easy, because where do you orient everything from, right? Like where do you actually orient? It's not as easy. So we'll deal with it. I'm just trying to point out direction is not as clear here in three-dimensional space as it is in two. Okay, so some more language about vectors here. I already told you that the name of the vector is this letter. Then you've got this little half arrow above it. It might be in bold. The tip of it is called the terminal point. The tail of it, which is this one, is called the initial point. Okay. And this is referred to as a displacement vector. That's what it's called, displacement vector. And ignore this, it just accidentally showed it twice. I don't know why it did that. Okay. Now, very important definition here. Equivalent vectors. Two vectors are said to be equivalent or equal if they have the same magnitude and direction. Position does not matter. So I have here two vectors for you. Those two vectors are equal. They're equal. They're the same exact things. It does not matter where they're positioned. What matters is, do they have the same length and do they point in the same direction? Well, I hope you agree they have the same length, because I just copied it and moved it, right? So do y'all see that they have the same length? Y'all agree with that? And that they point in the same direction means that if we were to kind of like orient this and then put an angle here, it should be the same as that angle there. So they have the same direction and the same length. So that's weird, because normally in two-dimensional space, if you move something, then it's changed. It's something different, but here it's not. And the reason this is important, and the reason why we use this in physics, is because, you know, let's say you're, let's say you've got a book. Okay, that's weird, my camera here. Okay, so if I have a book, and let's say it's sitting on a table, and I'm going to grab it and start pulling it across the table, I'm applying a force to it. And that force can be looked at as like a vector, right? That's pulling. And if I pull real hard, then the vector would get longer. If I change the angle that I'm pulling at, right, that's going to change the vector also. So we have a direction and we have like a force that we pull with. So when I move the book, this vector has moved also, right? But we don't want it to lose its value. We want it to still be the same as it was when it was over here. So that's why vectors are so important, because as you move something around, this isn't physically changing. It's still the same thing the whole time as you're moving it. So it's an important aspect of vectors that they're equal regardless of where they are in the space, as long as you get magnitude and direction matching. Questions on that? All right, so determining a vector from 2 points. I always like blow over this real fast, but this is very important because students get this wrong all the time. All right, so in two-dimensional space, let's say somebody gives you two arbitrary points, A and B, okay? And we will label, let's say that A is the point x1, y1, and B is the point x2, y2. Now those are points, okay? Those are points in two-dimensional space. We can create the vector that goes from A to B, right? There is a vector that goes from A to B. And we can label, oops, we can label that, we'll just call it AB. We could have called it the vector V if we wanted to, but we're just going to call it the vector AB because it connects A to B. And the question is, how do we come up with the vector? All right, so we have some new notation. So let me get back up to here. The vector from A to B, right, is, now we're using this for the first time right here. These are called angled brackets. That's what we use to designate vectors. So the vector A to B will be the angled bracket. It'll be the second x coordinate minus the first, and then comma, the second y coordinate minus the first y coordinate. The order that you put these in matters. So if you're going from the point A to the point B, I have to scroll back down here. If you're going from A to B, then you're always going to take these points and subtract these points. Do not reverse that, or else your vector is going to be actually backwards. Okay, so that's the actual definition. Now, if you want to reverse it, if you want to look at the vector that goes backwards from B to A, now what you do is you take these and subtract those. So that would look like this. The vector that goes from B to A would be, now you do the x1 minus x2, and the y1 minus y2. You don't, so many students miss points and miss major problems on problems down the road because they continually just not pay attention to the order there, all right? And that can mess so many things up. I'm gonna do a specific example, all right? I'm gonna do a specific example. This is just for us to kind of see the new notation and then what algebra is required. I'm gonna do the example first, and then I'll go back to three-dimensional space. Okay, so, oops. I want to do an example. So I want us to find the vector from the point, let's say -1, 4 to the point 5, 7. All right, that's the question. It's for us to find the vector that goes from that point to that point. So in a picture, -1, 4 is like about there. And 5, 7 is about there. And we're trying to find the vector that goes from there to there. And we can call it anything we want. All right, so I'm going to call it V. What it should be equal to is this angle bracket. Now, Jared, what's it going to be here? What minus what, Jared? Is Jared here? Oh, okay. All right, how about Katie?
It'd be for the x coordinate 5 minus -1, and for the y coordinate 7 minus 4.
Yeah, 5 minus -1, and then 7 minus 4. So this would be the vector 6, 3. Okay, so angle bracket 6, comma 3 is the vector that connects those. Good. Now, this was all two-dimensional space. In three-dimensional space, if you have 2 points, x1, y1, z1, and then a second point, x2, y2, z2, it's the same operation. To find the vector from A to B, you take the second x, subtract the first, and then the second y, subtract the first, the second z, subtract the first. And if you want to go the other direction, you reverse the subtractions. And that will give you the three-dimensional vector connecting the points. So let's do this one. I'll call on, how about Damien? Is Damien around?
Yes, sir.
Okay, Damien, I want you to do this one, the vector B to A. So tell me what's going to go in here.
Would that be 6 plus 2, comma, -5 minus 8, comma, 6 minus 10?
What do y'all think? Do y'all agree? Disagree? We're going from B to A, right? So we're going from the B to this one, which means you'll always start with these and subtract these. So it should be the 6, take away the -2. Yep. -5, take away the 8. And then the 6, take away the 10. This is correct. So this should be 8, -13, -4. Okay. Good. Any questions? I know a lot of you have seen vectors already, so I'm sorry, but it's in the curriculum. All right, now there is an important vector that you should be aware of. It's called the 0 vector, and it is written with a 0 and an arrow over it. This is not equal to the number 0. This is a number, and this is a vector. Not the same thing, okay? In fact, if you write down the zero vector, you would have to know what space you're in. So the zero vector in two-dimensional space right here is actually, it's got 2 zeros in angle brackets. In three-dimensional space, right, you've got 3 zeros in angle brackets. If you were in four-dimensional space, you'd have 4 zeros in angle brackets, and so on and so forth. So what about in one-dimensional space? What would the zero vector look like in one-dimensional space?
Just 1 0 in brackets.
Yeah, 1 0 in the angle brackets. That's what the zero vector is. Now, how long do you think the zero vector is? What's its length?
0.
0.
0, okay. What about direction? That's a little tricky. The zero vector doesn't have a direction. And that's kind of weird because we initially said that a vector is anything that has, you know, magnitude and direction. So the zero vector has 0 magnitude, 0 length, but the direction, you can't really say it has one. So this is a special vector. It's still a vector, but it's different than all other vectors in the sense that it doesn't really have a direction. You could say it's in every direction almost, right? Or you could almost argue that it's in no direction. All right, so more terminology. When you have a vector, you're always going to have angle brackets, and then you're going to have something in here, a number and a number. So we like to label those maybe like V1, V2. Instead of like A and B, we'll just say like V1, V2. These things have names, and they are components. So this is called the X component, and this is the Y component. And this is important in this sense. Let's say I write this down. What is the difference between these two things? What is this first thing, and what is this second thing? So what's 2, 3?
A coordinate.
That's a point, right? In two-dimensional space, right? Is a point. And these numbers are called the coordinates of the point, the coordinates. Here, this is a vector, right? And yes, you could go out 2 and up 3, and you could draw this vector, but you could also draw that vector over here, or over here, or over here. It doesn't matter as long as it's same length, same direction. All of these are equivalent. So we don't call these coordinates of the vector, we call them components. And that way you're not confusing points and vectors because they're obviously not the same thing. Okay, now this goes for 2 and 3-dimensional vectors. You either have the X component, Y component, or you have the X, the Y, and the Z components. So just language here. Okay. All right. I think, you know what? I think this is a good time. I think this is a place for us to stop. We still have a little bit of time, but I wanted to save the last few minutes for any questions that people might have about where they go to do their homework, like what homework am I supposed to do? So I can show that to you right now, just to be clear, but does anyone have any other questions that I can address before that? We're okay. So our schedule today, we were supposed to cover 3D coordinate system. And next time we're supposed to start with vectors, which we've already started. But trust me, any time that we can gain now is going to be worth it later. All right. So for tonight, what I would expect that you do is this homework. And let's see, we meet on Mondays and Wednesdays, right? So I would definitely expect that the homework from today, you have it done by Monday. All right. Now, homework that I give on Monday, I would like for you to be done by Wednesday before we meet again. Realistically, though, some of you have, jobs and you're busy. but you shouldn't drag it out too much longer. All right, so we get to, here's our main course. So you're going to go to this WebAssign and you're going to put in this code. And let's see if this works. So you go here, click on enter class key, and then you'll have to register, just put your name in and all that, and then you'll be logged in. Now let me see, I'll be able to tell if any of you have done this yet. Three students have done it, okay. So let me go to student view. When you come here, this is what it should look like. The only reason you're here is to get access to the electronic version of the book. That's the only reason you're here. So you're going to go to the ebook. And then from here, you're going to, let me bring the schedule back up. You're supposed to do the 3D coordinate system. It's 10.1. Ignore the page number because I don't think the page numbers match. But just go to the 10.1 exercise and do number 2, 3, 7, 11, 13. So let me go, where are we? 10.1 exercises, okay? And you're supposed to do number 3. Oh, 2, 2, 3, 7. So 2, 3, 7, 11, right? Those are problems. Now, when you're doing those, if you're having any trouble, this is where you go to the homework solution videos here. And you click on 10.1. And this should be me working through, I would say 90%, 95% of the problems I do on video. Sometimes I skip if the topic is close enough to something I've already done. I'm like, I'm not going to do another one of those, you know, but it's me working through those. So my recommendation is to use those videos as like a guide. See how much you can do on your own. Maybe watch my video, see if we're on the same track. You know, don't just watch my video on double speed and be like, yeah, I could do that. I could do that. You still have to get down there and get, you know, your hands dirty with this. And these videos, you know, the first one is only, what, it's about an hour. Then the second one's about 30 minutes. And then you can see they start to pick up a little bit. Some of them are shorter. Now, some of those aren't that bad. So anyway, that's the idea. You come here, we go through the topics, you go try and do your homework, you go there for help, you can come to my office hours, you can text me or whatever if you need assistance, and we just crank away at this. All right. You got anything for me? Okay.
I still have my hard copy of the book.
Oh,
So
great.
do I even need to like go online to do that, or?
No, you won't need to get on WebAssign at all. If you've got the hard copy, you can just work right out of the book. But
Okay.
nobody has to pay for access to that website.
Right.
It should be free, or not free. It was included in your tuition. They started to do that a few semesters ago. I'm not a big fan of that because it forces you to pay for something that you may already have a book for, or, you know, but
Right.
that's a decision that was made somewhere else, not my decision. So yeah, so you should be good with the book. You have this book right here, right?
Yep.
Yep. Okay. Second edition of Essential Calculus. And all that information for that book is in the syllabus. If you want to get it, if you want to go find it online somewhere, I'm sure it's pretty cheap because we've been using this book forever. So used versions are probably like $12 or something. My office hours.
I'm not sure if I missed this, but are we turning in this homework?
Nope. Nope. The homework is just for you to practice. But remember, the homework, look, your midterm and final, those two tests the problems will be similar to your homework problems. Okay. So in terms of level of difficulty, your midterm and final will be nothing outside of the realm of what you did for homework. with that said, everything that you do for homework is fair game. So you should do your homework, right? Now, the mini exams, those are the ones where I made the mini exams so that you can't go on Google and look it up. Like you're gonna have to do a lot of work to go try and find an answer. You know, it's not, these problems were just intentionally made that way. So, but if you can do them, it really shows that you understand the underlying concepts. Yeah. Anything else? Okay, well, I will definitely try and get through everyone else's names next time. We'll get into 10-2, and soon, before you know it, we'll be deep in this, right? So, okay, everyone, have a great weekend. Thank you for your participation. I will see you next week.
Yes, sir. Thank you.
Okay.
Thank you.
Sorry about that. I have one more question.
Oh yeah, what's up?
For the homework assignments, do you have to turn in written work, like the problems worked out?
No. Not for the homework?
Yeah. Yes, sir.
No. Look, if you choose to not do a single homework problem, I can almost guarantee you're not going to pass this class. I mean, I can pretty much guarantee that's not going to happen. So I would hope that every student here realizes by Cal 3 that you've got to do your homework, right? And I provided you the solutions so that you have that extra help if you need it to get through the problems. But I'm not going to collect it for a grade because I've already provided you the answers. So I don't want you to just sit there and write everything down just so you can go turn it in to get a grade. I'd rather you do, how do I put it? I'd rather you do 70% of the problems and you learn that than you to do 100% of them just copying my answers to turn it in for a grade. Does that make sense? Like it's really about you learning more than anything else. So
Okay, I
yeah,
understand.
so don't worry about me collecting it.
Okay.
Okay.
All right. Have a nice day, sir.
Okay. All right, everyone. Have a good one.